Yeah, thanks, Markus. Also welcome from my side. For those of you who don't know me yet, my name is Carsten Tellmann and I work for Gdata. That's an antivirus company located here in Bochum. And we are supporting this course since a few years now. And yeah, what does it mean we support this course? Basically, we offer an additional evening event every time we have an invited speaker here. And I'd like to invite all of you, if you like, to join us. Here you can see the details. We will have delicious dinner and drinks and a cozy atmosphere. And if you like to talk to Mathias a little bit more in detail about the topics he's presenting today, or his work in general, or every other stuff, or if you like to get in touch with the people working in the technical field of the antivirus company, that's a good chance. And yeah, if you have any further questions or like to have more details, don't hesitate to come to me after the talk. Yeah, and then now I think Mathias will introduce himself a little bit. Yeah. So that's it.
Okay. Can we maybe dim the lights? I think it will be more visible. Yeah. Or oh, I need. Is it over here? I don't want to do anything like. Yeah.
I will fix it.
Better. Awesome. Yeah, maybe this one is annoying. Oh. And that is how I hacked the university. Yeah.
No.
So, Mathias.
All right, so thanks all for coming here and welcome to this session on hacking with Unicode. And when I say hacking, I do mean the elite type of hacking, as you can see here. Now, so first let me introduce myself. I'm Mathias Bynens. I used to be a freelance front-end web developer. I live in Belgium, but nowadays I work for Opera Software. I work in the developer relations team, and my job requires me to have certain knowledge of web standards, so roughly everything that has to do with HTML, CSS, and JavaScript. And I also need to know about weird edge cases and how browsers treat these. And for a long time, I did a lot of research in that area. I even did it in my spare time just for fun. But over the years, I realized that this sort of knowledge has kind of an overlap between the kind of knowledge that a good hacker needs in order to attack web browsers or find vulnerabilities in web applications. So that's what I will be talking about today. I'll talk about some of the things that I learned about Unicode and everything related to that over the years. So first, briefly, I'll explain the basics of Unicode and character encodings, just so that we're all on the same page. Don't worry, I won't make this too long. And then we'll look at how JavaScript specifically handles Unicode and what kind of bugs that this often leads to. Then we'll also do the same thing for the MySQL database software. And finally, we'll take a look at some real-world exploits that are based on this knowledge. So first, let's take a quick look at the basics of Unicode. The first thing to remember about Unicode is that it is not a character encoding. People very often confuse UTF-8 with Unicode, but they're not the same thing. It's like comparing apples with oranges. Actually, it's not like comparing apples with oranges because they're of the same type. It's like comparing apples to zombies. So it's actually, Unicode is not an encoding. Keep that in mind. It's easiest to think of Unicode as a database instead. A database that maps any symbol that you can think of to a unique number for that symbol called its code point and to a unique canonical name for that symbol. And the main idea here is that you can now refer to specific symbols without using the symbol itself. You can just refer to its code point or to its name, and then everyone will know which symbol you're talking about, or they can look it up in the Unicode standard. It's a very basic idea. So for example, Unicode maps the Latin capital letter A to the code point U plus 0041. Now, note that this is a hexadecimal number, so it's not a decimal number. And usually, code points are formatted this way. So they start with a U plus prefix, and then they're followed by hexadecimal digits, which are usually 0 padded up to at least 4 digits. Now, another example is the Latin small letter a. This is a completely different symbol, and for that reason, it gets its own name and its own code point, which is a different value. So I think you start to get the idea now. Each symbol simply gets its own name and its own code point. It's as simple as that. But there's a lot of weird stuff in Unicode. For example, there's a character that is called a snowman symbol. And I'm not sure why you would ever need this, but it's there if you want to use it. And then there's other stuff, like everyone's favorite Unicode character, the pile of poo. And I'm not making this up. There's actually a big standard, an official standard called the Unicode standard, which includes this canonical name for a character, pile of poo. Look at that. Now, this is how it renders on a Mac or on an iOS device. So, of course, rendering of any character depends on your font and your system settings, but this is what it looks like on my computer. And as you can see, the code point is 1F4A9. So now it consists of 5 hexadecimal digits. Now, you may be wondering what the highest possible code point value is at this point, or how many code points are there in Unicode. Well, the possible code point values range from 0 to 10FFFF. So that's a little over 1.1 million possible symbols. I say possible symbols because not all of these code points have been assigned symbols yet. Most of them are just reserved for use in the future. So for example, when there's a new currency introduced tomorrow and people make up a new symbol for that, people can just add it to the Unicode standard by choosing any code point that has not been assigned a value yet. And then any existing encoding that supports Unicode will be able to represent that new character. So this means that Unicode is forward compatible, basically. Now, to keep things organized, all these code points are divided into 17 planes. And each plane consists of 65,000 symbols each, or code points each. And the first of these planes is probably the most important one. It's called the BMP, or the Basic Multilingual Plane. And I said it's the most important one because it contains all the most commonly used symbols. In fact, when you're writing a text document in English or even in German with all your weird umlauts and stuff, you probably won't need any code points outside of the BMP range. And just like any other range or any other plane, it consists of about 65,000 symbols, as you can see here. Note that the highest possible value for the BMP code point is FFFF, so all the BMP symbols can be represented with a code point that consists of only 4 hexadecimal digits. Now, there's a group name for all the other ranges as well, and these are called the supplementary planes or the astral planes. Keep in mind that in total, this is a little bit over 1 million other code points. So this is 95% of Unicode right here. So astral code points, because of this, are very easy to recognize because you can just look at the code point value, and if you need more than 4 hexadecimal digits to represent the code point, well, then it's an astral symbol. So is everything clear so far? Does everyone follow here? By the way, if you have any questions or anything is unclear during the talk, feel free to raise your hand and tell me about it. It doesn't say anything about you guys. It just means that I'm not doing a good job explaining stuff. So please help me out in that case. All right. So now we have a basic understanding of what Unicode is. So now let's talk about character encodings that support Unicode. These are all the encodings that fully support Unicode. As you can see, there's not a lot of them. And what do I mean by full Unicode support? Well, it simply means that they can encode or decode any Unicode code point. So this table shows the number of bytes each encoding requires for each code point. And one of these encodings in the table is a fixed length encoding, a fixed width encoding. Which one is that? Yeah? Exactly, UTF-32. So as you can see, it uses 4 bytes to encode any code point. It doesn't care what code point it is. It will always take up 4 bytes. So as a result, this is not a very efficient encoding in terms of storage space. There's also UTF-16, which is slightly better, as you can see. It uses 2 bytes for all the BMP code points, but for astral symbols, it uses 4 bytes. Still, this is an improvement over UTF-32, but we couldn't do better. And actually, the most ideal solution is probably to use UTF-8 whenever you have the choice. As you can see, there are several reasons for that. For starters, it supports all of Unicode, just like all the other encodings in the table. But another reason is that UTF-8 is optimized for storage space. So the most commonly used symbols take up fewer bytes. So as you can see there, the first range of code points, those are the ASCII symbols. So as long as you just use ASCII symbols, it only needs 1 byte to encode each of those symbols. And this also means that UTF-8 is fully backwards compatible with ASCII. This means that if you have an existing ASCII document, you open it and you resave it with the UTF-8 encoding, you would get the exact same document. So a lot of existing content on the web uses only ASCII, for example. And because this is by definition also valid in UTF-8, that's a big deal. Now, if you want to find out how these encodings work, it's very tempting to just Google for the name of the encoding, and then you'll probably find a document like this. This is an RFC, or a request for comments document. It's published by the IETF, or the Internet Engineering Task Force. And for example, the document we're looking at right here is the RFC 3629, which defines Unicode. Now, however, most of the time you don't really care about how the encoding was originally designed. What's far more interesting is to see how these encodings are actually implemented in real-world software, like in browsers, for example. And luckily for us, there's a different document that has all this information. It's called the encoding standard. And rather than a theoretical design spec like those RFCs are, this document is actually based on existing implementations of the encoding. So this is especially interesting if you're targeting a browser and you want to find out how it deals with a certain encoding. And yes, sometimes there is an actual difference between what the RFC says and what this document actually says. So for example, UTF-8 was originally designed to support code points up to U+7FFF, which is a very high code point value, and it's way outside of the range of what Unicode supports. And as a result, implementations don't really implement this at all because no such code point exists. So that's one of the reasons why you should always use the encoding standard instead of looking at the RFCs. It's based on real-world implementations. And as a hacker, that's what you're interested in. Now, this encoding standard also contains information on many other encodings, most of which don't support full Unicode. And here's just some of them. This is just a subset. These are not all of them. These are just the legacy single byte encodings. Browsers have to support these encodings for compatibility reasons. And my computer is crashing. Awesome. OK. So yeah, this was supposed to be a movie, but I guess it's too much to handle. Or maybe that PDF you were showing did have an exploit in it, and that's what I'm seeing now. Knew it.
You were not quick enough, so.
Yeah, so, well, the same rules apply here. The actual implementations, they usually differ from the original RFCs. So if you ever need to know how ISO 8859-2 works, don't look for an RFC, look for the encoding standard and go from there. So anyway, remember about the encoding standard I was telling you about? Yeah, it's really awesome, and you should all check it out. And it has all these single byte encodings as well. And if you ever need, oh, there it is. That's the movie that crashed the whole thing. It's so amazing. It's like 1 megabyte in size. Anyway, so the same rules apply here. The actual implementations usually differ from the way they were originally designed, and browsers implement them in a different way because of compatibility issues. So if you ever need to know how such a legacy single byte encoding works, read this document. If you ever need to do the encoding or decoding yourself, you can, for example, use these JavaScript packages. Is anyone familiar with Node and NPM? Just do a show of hands. OK, some people. If you're not, just Google NPM and then search for legacy encoding. And then you find a bunch of packages, and it allows you to encode and decode all these things. OK, it's good that some of you are familiar with Node.js and NPM. Are the other people familiar with JavaScript at all? Let's do a show of hands. Yeah, some experience with JavaScript. OK. So the next part of the talk will be kind of in-depth. We'll talk about various problems involving Unicode and JavaScript, and some common mistakes made by JavaScript developers, and also how they can be fixed. So even though this section is about JavaScript, other programming languages might have the same problems. So my advice is don't get too hung up on the language-specific details here. Instead, try to think of the underlying problems, because that's really the big picture that I'm going for here. So first, does anyone know who this guy is? You can shout. No one? Come on, guys. Yeah, Jay-Z, of course. Everyone knows it. He's a famous rapper. But a little known fact about him is that at some point he decided to write a JavaScript program. So he installed Node.js and installed NPM and started programming away. But at the end of the day, instead of having written a program, he had written a song about his frustrations with the language. You may have heard of it before. It's called 99 Problems. Now, don't get me wrong, I love JavaScript. It's my favorite programming language. But just like with any other programming language, unless you know all the gory details and the weird quirks by heart, which no one really does, you're just going to be surprised every now and then. That's just how it goes. And that's also the reason why we have websites like phpwhatthefuck.org, which documents these weird quirks of the PHP language quite nicely. And we also have a site for JavaScript called whatthefuck.js, which does the same thing, really. It documents all these weird, confusing behaviors without explaining it. And of course, all these weird things can perfectly be explained. For JavaScript, you can look at the specification and go from there. For PHP, you can look at the implementation and read the source code and go from there. But even then, even if everything can be explained, if a particular behavior of a language is confusing to a lot of people, then this is a bit of a problem. And I'm going to go ahead and say that JavaScript has a Unicode problem. The way JavaScript handles Unicode is surprising, to say the least. And I didn't actually know about most of the problems I will be talking about until I started working on Unicode.js a couple of years ago. In case you don't know what Unicode is, well, this video, which doesn't crash my computer, by the way, yay for that, neatly illustrates it. So Unicode is the name for the algorithm that all browsers and other software that deals with URLs has built in. And Unicode is the conversion between an internationalized domain name, which contains special characters, and it converts it somehow to a pure ASCII implementation. And then that's the domain name that you would register. So for example, if you wanted to buy mañana.com, you would actually have to register the domain name on the right-hand side. That's the Unicode algorithm. So just for fun, I wanted to make a JavaScript implementation of this algorithm. This algorithm is well defined. There's also an RFC that defines this. So I figured probably very simple to implement this, right? I mean, the algorithm is right there, so you just write the code that implements the algorithm and you're done. But while I was implementing it in JavaScript, I learned a lot of new things, and that's what this talk will be about, really. So for example, now that you know about Unicode, you may have seen some of these things before. The ECMAScript specification calls these hexadecimal escape sequences, which is kind of a weird name because most of the escape sequences in JavaScript use hexadecimal digits in some way. So anyway, in a string, you can have a backslash followed by x followed by 2 hexadecimal digits. And now that you know about Unicode, it's clear to see that this just refers to a Unicode code point. So this gives you a way to use a symbol in a string without actually using the symbol itself. This is fairly useful, well, not in these examples, but in some cases where you need control characters, for example. But in this case, we're limited to just 2 hexadecimal digits. So we can only really use this for code points up to 00FF. Luckily, there's another type of escape sequence called the Unicode escape sequence. And it starts with a backslash followed by U, and then it's followed by 4 hexadecimal digits instead of 2. So in other words, this can be used for all code points in the BMP, in the basic multilingual plane. And now that we have 4 characters, we can actually escape much more characters like this one, which is the white heart symbol. So this is much better already. We can use this for all the BMP code points, but what about all the other planes that we talked about before? What about the astral code points? We need more than 4 hexadecimal digits for those, right? So how do we solve that problem? How do we escape them? Another way to phrase the question is, what about the pile of poo? And other equally important symbols, of course, astral symbols. So the answer is, we can escape them, but it's kind of complicated. In ECMAScript 6, it will be really easy, actually, because they introduce a new type of escape sequence called the Unicode CodePoint escapes. Now you have a backslash followed by U, followed by braces. And between those braces, you can use up to 6 hexadecimal digits. So this is enough to represent any Unicode symbol. It's really easy too. The only downside is that it's a new feature and it's not implemented anywhere as of this moment. So if you want something that works today, the unfortunate solution is to use this thing called surrogate pairs. Yep. So for example, if you want to escape the pile of poo in a way that works today, you actually need 2 separate escape sequences. And these form a pair that only when they're combined together, you get back the original astral value. Now, there are formulas that can be used to calculate the code points for the surrogate based on a given astral code point, or to do the reverse operation. So to calculate the original code point based on 2 surrogate pairs. And here's a JavaScript implementation of those formulas. Now, you don't have to remember this formula, but you need to know that it exists, apparently, if you want to deal with Unicode and JavaScript correctly. Now, anyway, the whole concept of using just a single escape sequence to represent BMP symbols, but then using 2 escapes for astral symbols, that's a bit confusing. And it has lots of annoying consequences too. So let's say, for example, that you want to count the number of symbols in a string. My first thought would be to use the length property of the string. So in these examples, as you can see, the length happens to reflect the number of characters in the string, which is probably what you would expect. And this can be explained because if you escape each character in the string and then you count the number of escape sequences that you need, you'll see that there's just 1 in each of these strings. So this makes a lot of sense. However, if we try slightly different symbols, in this case, I'm using the mathematical bold capital A and mathematical bold capital B, which have different code you can see. And these are astral symbols. And now if you get the length of these strings, you'll see that they have a length of 2 instead of 1. And this is because JavaScript exposes these surrogate halves as if they were separate characters, kind of. And this is really confusing because we're human beings and we generally think in terms of Unicode characters or graphemes. This is my reaction when I first found out about this behavior. Yeah. So similarly, a string containing only the pile of poo has a length of 2 in JavaScript because it is an astral symbol. And there's a very obvious joke to be made here. But instead, I'm just going to show you a real-world example of where this breaks things. So this is a bug. It's not a security-sensitive bug. We'll get to that later. So this is Twitter a while ago. You know, they allow 140 characters for each tweet. And on their front end in the website, they just use JavaScript. And at some point, they use the length of the string to calculate how many characters you had left. Now, in their backend, they don't care if you use an astral symbol. It just counts as a single symbol. But as you can see here, for each pile of poo you enter, the counter decreases in steps of 2 instead of 1. So because of this bug, you could only ever tweet 70 piles of poo at once. It was a terrible bug. Now another example is this library, Countable.js. All it does is it adds live paragraph, word, and character counting to an input field on your HTML page. And then it displays those numbers elsewhere. So the first thing I did when I saw this demo page was, of course, to enter a pile of poo. And unsurprisingly, it counted it as 2 separate characters. So these are just some examples to illustrate that it's an honest mistake to make. So I don't blame the developers. But really, a lot of developers don't know about this or don't seem to know about this. I'm sure that they want to fix these issues, but they're just not aware of them. And that's, of course, an opportunity for hackers. Now, entering that pile of poo in that forum there, it kind of felt like this. Because I just almost knew that something would go wrong, because this is really such a common mistake. Yeah. So getting back to our question, how can it be done? How can we accurately count the number of symbols or code points in a JavaScript string? Well, one thing you could do is you could use a third-party library. For example, the Unicode library that I was talking about, it exposes some helper methods because I need this functionality as part of the library. And I also exposed it so that other libraries can make use of it if they need to without having to write the code again. So what you could do is you could pass a string to the Unicode UCS2 decode method, and that would turn the string into an array of code points. The resulting array would only have a single item for each code point in a string. So it would actually take care of these surrogate pairs for you. So if you then get the length of the resulting array, you get a more accurate result. Now in ECMAScript 6, there will be a standardized way to do this using 2 new features, actually. The first new feature is array.from, which is fairly obvious here. The second new feature that is being used here is slightly more subtle. This example also uses the string iterator. Whenever you pass a string to array.from, the string iterator will divide the string up into parts. And the string iterator is new, so it has been defined so that it only deals with whole code point values. So it takes care of the surrogate halves for you as well. So using this approach, you would get the same results, but again, this doesn't work anywhere yet. I've also made this tool that takes any string as input, and then it shows the escape sequences for any special characters within the string. So it's kind of similar to a hex dump, except that the output in this case is always valid JavaScript. So depending on what you're doing, sometimes this is actually more useful. So it's really easy to tell with this tool what kind of Unicode symbols a given string contains exactly, even if the symbols are non-printable or just white space. The link is there at the bottom if you want to give it a try. So getting back to our previous solution, and this, of course, depends on your use case. But if you're being really pedantic, there's a couple of other use cases that you need to consider. For example, in this case, JavaScript seems to be telling us that these strings are different, but visually they look exactly the same. So what is going on there? Well, I copied these two strings into the tool that I just demonstrated, and this is the output that I got. As you can see, the first string contains one symbol with code point F1, which is the N with the tilde character on top of it in a single symbol. Then the second string has a separate N character followed by the code point 0303. And this code point is the combining tilde. And these combining marks in Unicode, they just get applied to the previous character. So technically, they're two separate code points, but visually, they form a single glyph. So if you look at it this way, it's obvious to see why JavaScript tells us the strings are not equal. One string has 7 characters, the other has 6, and they use different characters or code points. So of course, they're not the same. But if we just want to count the number of characters in the string, we don't really care about all that. In this case, well, in both cases, we would expect an answer of 6, right? Because that's the number of symbols that we would count. So how can we make sure we get this expected result of 6 for both these strings? That guy was a little too enthusiastic. OK, so the answer is to use Unicode normalization. And this is another thing that is now part of the JavaScript language with ECMAScript 6. This is, in fact, already implemented in Opera and in Chrome. And as you can see, each string has a normalize method on its prototype. So you can use different normalization forms and then go from there. And this automatically takes care of these lookalike symbols that you saw before. Of course, after that, you still need to account for astral symbols or surrogate halves, just like we did before. But still, now our solution is even more accurate. Now, is our solution perfect yet? Well, it depends on your use case again. So if you want to handle things like this as well, like how many characters do you count here? I count 9 characters, or at least 9 glyphs. Now, what's happening here is these are a lot of combining marks that all get applied to the same symbol. That's why it looks so weird. So this is just basic Unicode stuff. So let's say we want to get the result of 9, but let's try our pedantic function that we used before. We actually get 116. Yeah, and I can see why that happens. Well, if you need to support stuff like this as well, the only solution is to use a very epic regular expression that strips out all the combining marks and grapheme extenders and then takes the length of the resulting string. Also accounting for lookalike symbols and astral symbols, just like we did before. I'll show you how to do this later. Now, another example that's interesting to think about is reversing a string in JavaScript. A very common solution to this problem is this one, where you just take the string, you split it so that it becomes an array of characters, then you reverse that array of characters, and then you join it back together. Yeah, sounds about right. And it seems to work in most cases. Like if you reverse ABC, you get CBA. Not bad. Let's try another one. If we reverse mañana, where the N is a single symbol with the tilde, then it still works fine. But if we try the other mañana, and we reverse that, then we see that now the tilde gets applied to the wrong symbol. Now, if you try to reverse an astral symbol, you will get the same astral symbol, but the surrogate halves will be in the wrong order now. So this is actually a form of data loss. The symbol won't be visible anymore in the reversed string. So even something as seemingly simple as just reversing a string quickly becomes tricky if you need to support full Unicode, and especially if you're using JavaScript. Now, luckily for us, a brilliant computer scientist named Missy Elliott came up with a bulletproof algorithm that accounts for these issues. The algorithm goes, I put my thing down, flip it, and reverse it. And indeed, by swapping the position of any combining marks with the symbol they belong to, as well as swapping the surrogate pairs before further processing the string, all these issues are avoided successfully. So thank you, Missy. I actually wrote a JavaScript library that does this, that implements this algorithm. It's called srever. So if you ever do need to reverse a string in JavaScript, you can just use it. As you can see, it accounts for these cases correctly. Now, it's important to note that this behavior affects other string methods too. It really bleeds through the entire JavaScript language. So some other examples of this are String.fromCharCode, for example. You can pass a code point to this function, and then it will return a string that contains a symbol that matches that code point. And this works fine for BMP code points, but as soon as you pass it an astral code point, you will get a result, but it probably won't be the result that you would expect. It gives something completely unexpected in that case. So the solution here is to actually use surrogate pairs and pass them as separate arguments. That's the intended solution. But of course, this is a pain because it means that you now have to calculate these surrogate halves separately, and you have to implement those formulas that I showed earlier. So another solution is to use a third-party library. For example, the Unicode.js helper methods can do this. You can pass an array of code points in there, and then it will turn it back into a string. And then you don't have to do the calculations yourself. But of course, it is at the cost of introducing a new dependency to your code, which is not ideal. And that's why ECMAScript 6 will fix this by introducing a new method, String.fromCodePoint. It's actually the same as String.fromCharCode, except that this one actually works for any Unicode code point and not just for those within the BMP. Does anyone have any idea why they decided to introduce new methods instead of just fixing the old ones? Yeah, you can put your hand up, or yeah.
Yeah, maybe you have libraries relying on this behavior, even though it's weird.
Yeah, exactly. It's been like this for ever since JavaScript was invented, basically. So all the content on the web relies on the old and broken functionality. So if we were to change it now, we would break a lot of stuff. And we cannot break the web. So that's why we have these new methods instead. Another example is the character add method on the string prototype. This is also affected by this behavior. So if you take the string containing just a pile of poo and you get the first character, so at index 0, you will only get the first surrogate half instead of the whole symbol, which may not be what you expect. Now for ECMAScript 6, I proposed a new method that does the same thing but deals with whole code points instead. Unfortunately, it was too late to add it to ECMAScript 6, but it's now on the roadmap for ECMAScript 7, so we might see it land in the language at some point in the future. If you want to use something like this today, you can check out the link at the bottom. It has a polyfill. Do you know what a polyfill is? Yeah, you do? Can you explain it?
For example, the picture element is not implemented in some browsers, and then you can import a JavaScript library and use the picture element.
Yeah, perfect. So a polyfill is a small script that you can use to use some new API that is not available in your browser yet. So this way you can use this already while supporting all the browsers out there. And another example is the character code add method. It has the same problem. Basically, if you get the code point of the first character at index 0 in the string with the pile of poo, you only get the code point for the first surrogate half, which is annoying because you would probably expect to get the code point of the pile of poo character. Again, in ECMAScript 6, this is now fixed by introducing string.prototype.codePointAdd, for which there's a polyfill at the bottom as well. And another example is how would you iterate over all symbols in a string in JavaScript? Because keep in mind that you have to deal with all these surrogate halves and you want to merge them together into a single symbol before you process them. Well, in ECMAScript 5, so in current environments, you would actually need a lot of boilerplate code just to handle these surrogate characters correctly. Note that this code example is not even complete yet. It doesn't handle lone surrogates correctly, so you would need even more code than what you see here. Now, luckily in ECMAScript 6, it will be much easier. You will be able to use the new for-off construct, which again uses the string iterator that I talked about earlier. So it iterates over whole code points instead of surrogate halves. So this will be much easier there. Unfortunately, this doesn't work anywhere yet, but give it a couple of months and browsers will probably have this implemented. Of course, there are much more examples. Basically anything that involves strings in JavaScript. So string.prototype.substring, string.prototype.slice, anything that involves strings. And another thing that involves strings is regular expressions. For example, the dot operator in regular expressions only matches a single character. But because JavaScript exposes surrogate halves as separate characters, it won't ever match an astral symbol. So I would expect foo.bar to match the string foo pile of poo bar, but it doesn't. So let's think about this for a second. What regular expression could we use to match any Unicode code points or any Unicode symbol? We cannot use the dot operator because that doesn't match astral symbols, and it wouldn't match line breaks either. We can solve the line break problem by doing something like this, where we match all the white space characters and then match all the non-white space characters too. So then we match all the characters, but still it wouldn't match whole astral symbols because those are two characters as far as JavaScript is concerned. So any ideas? What would the regular expression look like to match any code points? Yeah, it looks something like this. Yeah, my thoughts exactly. So the first part of the regular expression matches any BMP symbol that does not start a surrogate pair. And then the second half of the regular expression matches a surrogate pair. And then the last part just matches lone high surrogates. So the surrogates that usually start a surrogate pair in JavaScript, but that appear on their own in a string, which is allowed in JavaScript. So of course, these are not the type of regular expression that you want to be writing by hand, let alone debugging them. So what I did is I used a library called Regenerate to generate these for me. And this is how I did it. So it's just a simple line of code. I create a new regenerate instance. I call add range. I add the entire range of code points to the set, and then I call toString on it, and then it returns a string that can be used as part of a regular expression literal in JavaScript. Another example that's maybe a bit more advanced, create a new instance, add all the existing Unicode code points to the set, then we remove a range of symbols based on their string values, in this case all symbols from A to Z. Then we remove a single character, in this case the pile of poo, from the set, and then finally return that into a regular expression. Any ideas what this will look like? Yeah, me neither. Well, apparently it's this. So again, this is not a regular expression that you would like to write by hand or have to maintain by hand. I mean, even just adding a single symbol to the set of characters that should be matched would be a pain. So if I had to choose, I would much rather debug the 5 lines of code right above the regular expression. So my advice is, if you ever need to do something like this, create a small build script that just has these 5 lines of code and that generates a regular expression for you. That way it's easy to just add or remove some code points from the set and change the regular expression that way. Another example that's maybe a bit more real world, I don't know, is let's say you need a regular expression that matches all Greek symbols in the Unicode standard. Well, there's good news in that case, because I published a bunch of NPM modules that contain the data for each Unicode category and script and block and property and all the other Unicode data. So if you combine these data files with Regenerate, you can very easily create complex Unicode-aware regular expressions. In this case, the regular expression looks like this, in case you were wondering. Now, ECMAScript 6 kind of fixes this by introducing a new flag for regular expressions. This is the U flag. And this magically makes the dot operator match whole code points instead of surrogate halves. Another example is character classes. So whenever you have, for example, a character class with a range from A to C, you expect it to match the characters A, B, and C, right? That makes sense, because that's the order the characters are in the Unicode standard. So similarly, you may expect this regular expression to match the pile of poo, the flexed biceps, and the dizzy symbol, right? Well, it turns out it doesn't really work that way. Actually, we get an error on the very first line of code there on the regular expression. We get syntax error, invalid regular expression, the range is out of order in the character class. Why is that? Well, as far as JavaScript is concerned, this is what that regular expression looks like. You have two surrogate pairs there. So what JavaScript is now trying to do is create a range from the low surrogate for the first character and the high surrogate for the second character, which is not the range that you wanted to match. And because this range is in the wrong order too, it throws this error. So even if this would work, it would still not be what you wanted. Now, in ECMAScript 6, this is easy to fix. That rhymes. So you can just use the U flag again, and that magically makes it work the way you would expect to. If you need something that works today, however, well, you're stuck with using a tool like Regenerate, for example. In this case, you can add a range of code points and then turn that into a regular expression. And as you can see, the regular expressions then deal with the surrogate halves manually as if they were separate characters, which is how JavaScript treats them as well. So in summary, it's pretty obvious that JavaScript has a Unicode problem, and these are just some of the problems that JavaScript developers are facing. And from my experience, most developers don't know about the issues at all. I believe they want to fix these issues if they're made aware of them, but it's just not well known enough. And that is an opportunity for hackers, of course. We can find lots of bugs this way, and who knows, some bugs might be escalated into exploits. So the main takeaway here is whenever you're pen testing a JavaScript application, be sure to enter a pile of poo or any other astral symbol in your vectors. And in many cases, there will be a bug of some sort. And in some cases, you never know, the bug will lead to a security-sensitive vulnerability. I have some examples of that later, but first, let's talk about MySQL as well, because it does have some problems with Unicode of its own. So let's say you want to use a MySQL database to store some text. You know UTF-8 is the preferred encoding, so you Google for some online tutorials, and you create a new table, and you set its default character set to UTF-8. And this is how you do that in MySQL. It's UTF-8 without the hyphen, because that's just how it works in MySQL. OK, so then you try to insert some data in the database, and everything seems to work fine until you try to insert a string that contains an astral symbol. So note here that the query doesn't fail. It doesn't throw an error. All you get is a warning, which means that most code on the web won't detect situations like this. The warning contains the UTF-8 encoded byte sequence for the pile of poo character. And it says that the string value is somehow incorrect. Now, if we retrieve the value from the database, we see that only foo was actually inserted. So MySQL's default behavior here is definitely a bit weird. So instead of throwing an error, it tries to insert the string anyway, and it just stops at the first astral symbol that it cannot handle. So effectively, the string is truncated at the first astral symbol. This is not what we want. And it turns out that MySQL's UTF-8 character set only partially implements UTF-8 encoding. It can only store UTF-8 encoded symbols that consist of 1 to 3 bytes. Encoded symbols that take up 4 bytes are not supported at all. So because astral symbols, I'm not sure if you remember from the encoding table that we looked at earlier, but astral symbols consist of 4 bytes in UTF-8, all of them. So you cannot store any of them in MySQL's UTF-8 implementation. It's kind of a scumbag. So the solution here is, if you have access to the database, is to alter the table and change the character set to this thing called UTF-8 MB4, which is actually real UTF-8. The MB4 stands for Mathias Bynens 4, because I requested this feature. Not really, it stands for multibyte 4, actually. So if you make this change and then you try the same thing over again, it will magically work the way you would expect it to. But still, this is another one of those things that a lot of developers don't seem to know about. So let's move on to the hacking with Unicode parts. That's why you're all here, right? So we talked about Unicode, character encodings, and their common problems in JavaScript and MySQL. We talked about combining marks in Unicode. So let's see some examples of where people use this knowledge to actually exploit bugs. So the first thing I want to talk about is, remember when I talked about encodings before? I told you to use UTF-8 whenever you can, because of following reasons. It can encode every possible Unicode code point. It's also backwards compatible with ASCII, and it's a very optimized and compact encoding. That's the reason that I gave you. But those are not the only reasons. It turns out that various other encodings have security issues whenever they're used with user-controlled content. So let's take UTF-16, for example. This is a proof of concept video. Well, I made the video, but the proof of concept was made by Henry Sivonen, who works for Mozilla. And he was trying to get his teammates to remove the encoding view in Firefox. Here goes. So this is just a simple web page. It contains some mojibake. Mojibake means garbled text. So usually due to encoding issues, that's what you see there at the bottom. So it takes a little bit of social engineering to change the encoding to make the user do that. And when you do that, it's actually a cross-site scripting vector. So let's look at it one more time. So at the bottom is the garbled text. It's just some weird Unicode symbols, Chinese or Japanese, I don't really know. And with just a little bit of social engineering, if you change it to UTF-8 or any other encoding, you get cross-site scripting attacked. Well, here's the relevant part of the hex dump of that file. So remember the encoding table? It said that UTF-16 uses 2 bytes for each BMP code point. So this is the relevant part. I highlighted it. And because it uses 2 bytes for each character, this is a single character as far as UTF-16 is concerned. This is this character. I mean, you can read the hexadecimal values, and that's just the code point value for the symbol. But as you can see on the right-hand side, if you actually interpret this as ASCII or as UTF-8, which is the same thing as ASCII, as far as ASCII characters go, then you actually get 2 completely different characters. In this case, the less than symbol and the S. Then the next UTF-16 encoded character is this one, but in ASCII, it's 2 characters. It's the C and the R. And I think you start to get the idea now. It just goes on like that. And this is a very easy way, once you look at the hex dump, to hide some content into a UTF-16 encoded file. So for this reason, you should definitely never use UTF-16, always use UTF-8. Now, Masato Kinugawa did something really similar. He found an endpoint on accounts.google.com where he could override the output encoding. So he could set it to UTF-32, for example, which is not supported in all browsers. It doesn't work in Firefox, and it doesn't work in Internet Explorer. So what happens when a browser gets a document that is encoded in an encoding that it does not understand? Well, it tries to decode it anyway using the encoders that it does know. So using UTF-8, for example. So this trick enabled him to create a cross-site scripting vulnerability on this page in Internet Explorer. And this is what the vector looked like. Yeah, well, the GIF was not actually part of the vector, of course, but still it looks really weird, right? Well, it can, again, be explained if you just look at the hex dump. The same principle applies here. UTF-32 takes up 4 bytes for each encoded character. So this is the first one of the relevant payload. As you can see, this is just this code point, 2200, but in ASCII, there are actually 3 null bytes and then 1 quote mark. The next encoded character is this one, code point 3E00. But if you look at it, if you decode that as ASCII or as UTF-8, it's actually, again, 3 null bytes and another character. So it just goes on like that for the rest of the file, of the payload. And the end result was this. So he had a cross-site scripting vulnerability on accounts.google.com. And all it really takes was the stuff I told you about before. It's actually not that hard once you understand this. So next example, do any of you use Spotify? Show of hands. Yeah, okay, some people, but I guess everyone has heard of Spotify, right? Yeah. Okay, so fun fact about Spotify, they allow almost any Unicode symbol in usernames. And so they don't limit you to just ASCII characters, which I think is great. I think more services should do that. But unfortunately, in Spotify's case, they had a small bug in their code, which allowed attackers to easily take over someone else's account. And the attack worked something like this. Let's say you wanted to take over the account with username Obama. Just an example. So what you could do is you could register the same username using lookalike symbols. Like in this case, I'm using Unicode modifier letters. That's why it looks so weird, like it's superscript. And if you did that, well, Spotify had a script upon registration that checked if the username existed already. But in this case, the script would say, okay, they're two completely different usernames, so go ahead, register it, which makes sense. There's two completely different strings, right? However, after logging into your new account with the password you chose, they accidentally performed Unicode normalization on login. So the result was that you would actually be logged in on the original accounts instead, the real Obama account. So it's, again, this is a really simple bug, but it can lead to some really bad security issues. Let's talk a little bit about JavaScript and JSON grammar. Is anyone familiar with JSON? You know what JSON is, right? It's this data format. Okay, well, imagine an HTML page where a server-side script injects some user input inside of a single line comment in a script element, like this. Also, it strips new lines, ASCII new lines, to prevent you from breaking out of the single line comment. So do you think this code is safe? Well, probably not, because else I wouldn't be asking, right? If you look at the ECMAScript specification, which is the official standard for the JavaScript language, it lists a number of line terminator characters. And these include the usual suspects like line feed and carriage return, but also these two weird and not commonly used symbols, U+2028 and 2029, line separator and paragraph separator. So because these are treated as line terminators, it means we can use them to break out of single line comments. So with that in mind, if we go back to the previous code example, now we see that this is actually a cross-site scripting vulnerability. If the user input contains a line of paragraph separator, then anything following that character will not be part of the comment anymore. So this is not a safe solution. And as a result, it also means that JSON is not a subset of JavaScript, contrary to popular belief. For example, well, not all JSON formatted text is valid JavaScript code, for starters. So if you have a string containing JSON formatted data, you can use JSON parse to unserialize it. And eval is unfortunately often used as a fallback for older browsers that do not have a JSON.parse implementation. But depending on which characters that the data contains, running the data through eval might throw an error. Of course, you shouldn't be using eval in the first place, but there might be other situations where you pass JSON formatted data to a JavaScript parser of some sort. And in such cases, you should always make sure that you escape JSON formatted data before passing it on. There's a tool for this called JSASK. It works in browsers, it works on Node.js. There's a command line interface for it. The source code is available on GitHub, so check it out. And here's how you would use it to create escaped JSON formatted data. It basically boils down to using JSASK instead of JSON.stringify. JSON.stringify is a standardized native method that stringifies your data or serializes your data as JSON. But as you can see, it doesn't really escape any characters unless it's absolutely necessary. So in this case, the resulting data would contain the raw, unescaped Unicode symbol. But if you use JSASK instead, the only difference is a single backslash, which means that it now contains an escape sequence for this character. So both strings are exactly equivalent after parsing them, after deserializing them, but one is much safer than the other. Now, another thing that can be useful for you guys is the fact that surrogates, they usually occur in pairs, right? And together they form a single astral symbol. But technically, they cannot be used on their own because they're not valid code points on their own. But JavaScript strings, for some reason, can contain lone surrogates. And the same is true for JSON strings, or strings in JSON formatted data. And the problem with that is that UTF-8 encoders, they must not support lone surrogates according to the encoding standards for security reasons. So because of that, attempting to store JavaScript or JSON strings in a database that uses UTF-8 might result in an error or even in a crash, depending on your application, unless you escape the strings first. So again, similarly as the previous set of advice, always escape JSON formatted data before passing it to a UTF-8 encoder. And no developer that I know really knows about this. So this is definitely an opportunity to cause some mayhem. So again, use the same library or something that you write yourself, I don't care. And here's how you would use it. Again, if you just use JSON.stringify or PHP JSON_encode method, it would just contain the raw and escaped symbol, unless you set a specific flag. But if you use JSS, JSON option enabled, it would escape the character correctly. OK, let's try another real-world vector. Has anyone heard of Fabricator before? Show of hands. No one? OK, that's OK. It's an open source project by Facebook. And they use it internally for their own projects, as well as some other big companies like DeviantArt, Dropbox, Radio, and Facebook themselves. They call it a software engineering platform, and it's kind of similar to GitHub, really. It hosts your Git and SVN repositories, and then it gives you a very nice interface that makes issue management and code reviews and stuff like that really easy. Now, user account registration requires an email address on a whitelisted domain. And of course, if you're the admin, if you installed Fabricator on your domain, then you can configure this completely. So for example, if you wanted to create an account on Facebook's private instance, you would have to have an email address that ends with @fb.com. Else, there's no way you would get in. And also, the confirmation email is sent to that address. So you really need to have an address there, or it's impossible to create an account. However, Fabricator is written in PHP, and it makes use of MySQL to store its data. It also, by default, makes use of MySQL's UTF-8 character sets by default. Really? Yeah, really. So what can we do about this? Well, let's say you tried to register your own email address, evil@hacker.com. It wouldn't work. It would give you this error message. So what we can do now is we just append an astral symbol, like the pile of poo, for example, and then we append @fb.com to it. So when we submit this form, the backend in PHP will validate this. It will see, OK, the string ends with @fb.com. Everything looks great. And then it inserts it into the database. The database will truncate that string. And as a result, your real email address will be the only value that is stored. So it's, again, this is really simple, but no one seems to know about this. And this led to a really nice vulnerability in their Fabricator product. My friend Tom van Goetem discovered this after I told him about this behavior in MySQL. And he got a well-deserved bounty for it. The same guy, Tom van Goetem, also discovered a 0-day in WordPress based on the same information that I gave him. And it could actually lead to remote code execution on some configurations. It's really interesting. So at its core, it was an object injection vulnerability due to unsafe unserialization. Well, actually, it's a bit misleading to say that, because the unsafe unserialization was not the cause of the vulnerability. So whenever data is read from the database or stored into the database, it goes through this isSerialized function. I slightly simplified it, but this is more or less what it looked like. So the data as retrieved from the database is usually a string, but it could also be a string that represents a serialized object, like an array or an instance of a class or a number or something like that. And in that case, it needs to be unserialized first. And the same thing goes when saving data to the database. If the data is not just a string, it needs to be serialized before you store it into the database, because else there's no way to store it. So here, as you can see, they have a check in place to see if the last character is not a semicolon and not a closing brace. In that case, there's no way that the data is serialized. And actually, this code here is perfectly fine. It's not vulnerable. The vulnerability lied elsewhere. I just wanted you to see this. So if it does not end with a semicolon or a closing brace, they return false. So just to recap, before writing to the database, the data should get serialized only if isSerialized returns true. And after retrieving the data from the database, it should get unserialized only if isSerialized returns true. And usually, when you store data to the database and then you retrieve the same data, it would return the exact same result. And isSerialized would also return the same result because it's the same string. But because WordPress, surprise, surprise, uses MySQL's UTF-8 by default, it is possible to save a string that ends in an astral symbol to the database, and then that string will get truncated upon insertion. So in other words, you insert a string that does not get serialized because it bypasses the isSerialized function. And then later, that astral symbol is dropped from the string, so when it's read from the database, then suddenly isSerialized will return true instead of false, and then it will deserialize your object. And this is where the vulnerability lies. So in practice, you could do something like this. Oh, sorry, there was a question?
Shouldn't the first true actually be a false? Because it doesn't make sense to serialize data if isSerialized returns true already.
Oh, yeah, you're absolutely right, yeah. Well, but you get the idea, right?
Yeah.
It's, yeah, good point. So you could actually abuse this if you just had a user account on any WordPress installation for which you do not control the server. You could do something like this, where you just go to your profile, you change a field like your first name, for example, and you actually add a serialized object there, in this case an array, and then you append an astral symbol like the pile of poo. And then when you click Update Profile, it will save that into the database. It will say Profile Updated, and then when it reads back that data, well, if it says array, it means it now gets deserialized, right? So this is the vulnerability that was part of the WordPress core. Now, how could you actually exploit this? Okay, there's definitely a vulnerability here. What can we do about it? Well, unfortunately, or fortunately, depending on how you look at it, there was no exploit available in the WordPress core. But of course, as you know, WordPress has lots of plugins. And some of the very popular plugins allow you to do something like this. Well, PHP has magic methods, right? Like wake up and destruct and toString. And these magic methods are automatically called when certain things happen to an instance object. And this means that we can construct a payload that unserializes into an instance of such a class. And then it will magically start executing code for us. Now, this could be any class in the WordPress core, but like I said, none of the classes in the WordPress core were vulnerable. But it could also be a class added by a plugin. So if just one of these classes has a magic method that runs some code for us, now we can suddenly trigger execution of that code just by entering our payload in the WordPress admin interface. And that's what the vulnerability was about. So Tom actually found a bunch of plugins, a bunch of very popular plugins that allowed you to combine this vulnerability into remote code execution. If you're interested in the details, I strongly suggest you read his blog post on the topic, because I really just simplified it here. But there's a lot of cool stuff in there. Go check it out. Now let's talk about Stack Exchange. Who knows about Stack Exchange? Who knows about Stack Overflow, the website? Yeah, okay. So Stack Exchange is the name of the network that runs websites like Stack Overflow and other similar websites. So at some point, Daniel Le Cheminot discovered that their HTML sanitizer was vulnerable to cross-site scripting. And to understand how the attack works, we should look at the C# code that did the HTML sanitizing. So for the HTML elements whitelist, they used this regular expression. So as you can see, they would only allow A elements, B elements, block quote elements, code elements, and so on. Does anyone spot the error here? Yeah, me neither. It looks all right so far. And the next part of the original source code had this very helpful comment. It says, leave the save HTML tags. And they actually went through the effort of putting quotes around the word save. It's almost as if they knew something was about to happen. And indeed, if we move on to the rest of the code, well, we see that they have some checks to see if it's an anchor element. Then they try to make sure that only the href and title attributes are used. If it's an image instead, they only allow source, width, height, and alt, which makes sense. Then the code goes on like that. And finally, if the string doesn't start with a or img, then they just return the HTML as it is. Then they think it's safe already. So did anyone spot the problem? Yeah, the problem is actually on the previous slide. So let's go back. Anyone? Yeah, I wouldn't have spotted it either. It's really weird. So apparently the starts with string method in C# performs some kind of normalization on the string before checking if it starts with the provided substring. So as a result, it was possible to bypass this if check and therefore skip the attribute filtering altogether using just something like, well, this. And in case you don't see it, it's right there. This is a Unicode combining mark. So remember when we talked about those? Well, after normalization, C# seems to think that the string is actually this instead. Like, see the little ring now gets applied to the G character. And because of that, the starts with method now returns false in this case, because it does not technically start with img without the ring on top of it. So in this case, the HTML is returned as it is already, including our cross-site scripting payload. And, well, that's how you hack Stack Overflow. So for more details, check Daniel's blog post. It's really good. I don't have any other examples for you, but remember, if you keep poking at your target for long enough, you might be able to turn bugs into exploits. And then something like this usually happens. And I personally really think that there's still a lot of Unicode-based bugs and exploits just waiting to be discovered. I definitely found lots of bugs, but I leave it up to you to find the exploits. That's the cool stuff. So thanks for your attention.